Natural Resources, Geology G4. This is video 2, the formation of metalliferous ores from igneous processes. This video looks at the formation of metal ores both by igneous and sedimentary processes. In the last video we saw that certain metals get concentrated in certain rocks called ores. This is an example of chalcopyrite. You can see the copper within it. The average crustal abundance of copper is 0.01%, and yet in order for it to be profitable it has to contain a grade of 2.2%. Now this means somehow that copper has to be concentrated in certain rocks. How does that happen? Well, there are two igneous processes that concentrate metals. The first is gravity settling producing cumulate layering. The second are hydrothermal circulations. Okay, gravity settling cumulate layering. Here we see a typical magma chamber beneath the surface feeding a volcano on the surface. Notice the feeder dikes where the magma pushes up into the empty chamber. Now, there's a full chamber of magma at roughly 1800 degrees. Nothing is crystallized, nothing is solid there at the moment. But let's just drop the temperature down to about 1400 degrees. And if we could see it, what we notice, there's certain crystals forming. Now, these crystals, until they're dense enough, will remain in circulation until they're heavy enough to drop out of circulation and form a layer at the bottom of the magma chamber. So, why is it that certain minerals crystallize at certain temperatures and then form this cumulate layering? Now this is all to do with Bowen's reaction series, which takes magma and the individual minerals within magma and looks at what temperature they start to crystallize. Notice here the high temperature minerals, olivine, starts to crystallize first, and then we descend down the order here towards potassium feldspar, mica and quartz, and these are the last minerals to crystallize. Notice as well, the first are ultramafic, the second are basaltic, andesitic, and then granitic. So there's an order of temperature and there's an order of silicity. Okay, let's apply that Bowen's reaction series to the cumulate layering and go through it again. There's our Bowen's reaction series. According to that, the first crystals formed will be olivine. So here's our crystals of olivine, around about 1400 degrees. Yep, there they form like that. Now, according to Bowen's reaction series, the next one will be pyroxene. So pyroxene is forming, and eventually they're dense enough to fall out of circulation to form a pyroxene cumulate layer as well. Now, in this way, an awful lot of cumulate layers can form within a magma chamber. The most famous cumulate layer, and probably the most profitable ever in the world, is the Bushveld complex in South Africa. Now, the Bushveld complex is famous for its platinum and chromite layers called reefs. Follows a short video about the Bushveld complex in South Africa.
The Bushveld complex of South Africa is the world's largest and most important repository of platinum group metals. It extends laterally over 65,000 square kilometers and is up to 8 kilometers thick. More than 2 billion years ago, the Bushveld complex was formed by volcanic eruptions that repeatedly injected molten basaltic rock known as magma or lava into a huge subvolcanic chamber inside the Earth. The cooling and solidification of the molten magma resulted in the formation of igneous rock. Because the molten rock was beneath the surface of the Earth, it cooled much more slowly than usual. By slow cooling, different minerals crystallized at different temperatures and accumulated as layers from the base upwards. With time, the weight of the cooled magma and the forces of the Earth caused the layers to sag down in the middle, giving them the shape of a pile of very thin saucers. Time and weather combined, eroding the landscape, moulding the surface of the earth. The central part of the saucer was buried under younger rocks, while the edges cropped out as two semicircular arcs of rocks. These outcrops are referred to as the eastern limb, from Sierkooigat through to Steelpoort, Leitenberg and Stoffberg. The western limb, from Tabazimbi to Pretoria, and the northern limb at Potgietersrus, now called Mokopane. The Bushveld complex extends over some 350 kilometers from Leidenburg in the east to beyond Rustenburg in the west, and 250 kilometers from north to south, forming a rough saucer shape that dips towards the center. As early as 1928, Dr. Percy Wagner had already stated that these are by far the greatest primary platinum deposits ever discovered, and their true magnitude does not as yet appear to have been realized. The Bushveld complex is renowned not only for its size, but also the persistence and regularity of the layering of its mafic and ultramafic rocks. To date, it also contains the world's richest known deposit of platinum-bearing ore, including all the precious group metals, as well as base metals and gold. There are three different ore bodies in the well-developed layering of the Bushveld complex, from which platinum is extracted. The first ore body, the Merensky Reef, has a width of 0.25 to 1.5 meter and is well mineralized with high platinum group metals or PGM values. It also contains base metals such as copper and nickel. In the early years, it was the only reef that was mined. Approximately 10 tons of Merensky ore, the equivalent of 2 hoppers, will yield 1 ounce of platinum. The second ore body is the upper group 2 chromatite layer, or UG2 reef. The UG2 is a thick chromite seam with a width of 0.6 meter to 1.5 meter and lies between 15 and 400 meters below the Merensky Reef, depending on where you are in the complex. It contains most of the PGMs and chromite, but is lean in base metals. Although it was originally identified in the 1920s, no attention was initially given to this potential ore body until the 1970s. It had to wait for the development of new metallurgical technology in the concentrator process. The UG2 reef is now a major source of platinum and is mined in places where the Merensky is not currently economically viable, or in sections where the Merensky has already been mined. Approximately 20 tons of UG2 ore are required for 1 ounce of platinum. The Merensky and UG2 chromite reefs can both be traced on the Earth's surface for over 300 kilometers. The third ore body, the Platte Reef, extends over 30 kilometers and has a thickness of up to 30 meters. Although platinum remains its primary product, its ratios for nickel, copper and palladium are higher than the Merensky and UG2 reefs. The world's largest open-pit platinum mine, PPL, now called Mogalakwena, has been operating on the Platte Reef since the 1990s.
Okay, so that was cumulate layering, which is linked to Bowen's reaction series. There's another igneous process that goes on at the same time, probably slightly later after it's been cooling, that forms minerals in certain locations, concentrates those minerals. And they're called hydrothermal circulations. Rainwater and groundwater seeping towards the magma chamber will be heated up, often much higher than their boiling point of 100 degrees. Some of this superheated water can get up to 500, 600 degrees Celsius. Now it mixes, it circulates within the magma chamber. Now as it's so hot, normal metals that it wouldn't be able to dissolve are dissolved in the water. And then the circulation pushes up through the dikes up towards the surface. Now these circulating fluids are called mineralizing fluids because they contain lots of minerals such as tin, zinc, copper and iron. And these flow out from the central point out through the veins towards the surface. Here you can see an example of a hydrothermal vein. This is a zinc layer in Germany which is caused by a hydrothermal circulation. Another common question looks at an intrusion. You can see here's our granite intrusion here, and there's our hydrothermal veins emanating from the intrusion itself. But what you might notice is that there's different layers within the veins. So take this vein here. The one closest here, this part here, will be rich in tungsten. Then further away, that same vein will be richer in copper, and further away again, that one will be richer in lead. So what causes this zoning? Let's look at a sort of basic model here. Here's an intrusion, here's our hydrothermal vein again. So it's moving out from the central point. Now this is to do with the order of solubility. Certain minerals are more soluble than others, so they will travel further away from the intrusion before they precipitate out. Now the example we just looked at, tin was the least soluble mineral, so it's the first to precipitate out closest to the intrusion, forming a tin zone. Then the next mineral on the solubility scale was copper, then lead, and the most soluble of all was iron. So let's have a look at that again. There's our source of heat, the original granite intrusion. Here's the hydrothermal veins. And in order of solubility, we said the least soluble was tin, tungsten, then it was copper, then lead, then iron.